Introduction to Microelectronic Fabrication, Problem 4.3. A boron diffusion with a resistivity of 1 ohm centimeters in an N-type wafer is resulting in a Gaussian or a drive-in profile with a given surface concentration and a given junction depth. Part A is asking how long is the diffusion if we're at an 1100 degree temperature. So first thing we can do is list the given equation for a drive-in profile, which is that the concentration is the surface concentration times the exponential of negative x squared over 4 dt. So if we think about it, we know the surface concentration, that's given to us right here. We know x, that's given to us as the junction depth. We are solving for t, and we don't know d, we also don't know the appropriate concentration. Let's start by solving for d. We know that d is equal to d naught e to the negative ea over ktk, right? D is the diffusion coefficient. To find it, we could use table 4.1, which for the appropriate element gives us d naught and ea. So if we have a boron, we have a d naught of 10.5, an ea of 3.69, and then if we look at example 4.1, we have the exact case that we need, right? So we have this temperature of 1100 that we also plug in, and we get 2.96 times 10 to the negative 13 centimeters squared per second, right? So if we do that ourselves, we get 2.5 e to the negative 3.69 over k, which is the Boltzmann constant, which is equivalent to 8.614 times 10 to the negative 5 times 1373. Why 1373? Because we're in Kelvin at 273 degrees, right? So that's just a little tip. Make sure to use the appropriate units. And we know that solves to be 2.96 times 10 to the negative 13th centimeters squared per second. Cool. Now we need to solve for the appropriate impurity concentration. And we know that it will occur at the junction depth of 4 micrometers. So how do we solve for it? Well, because we're given the resistivity, we could relate, using figure 4.8, the resistivity Rs, right? Rs to the impurity concentration. In our case, we have a resistivity of 1. We know it's an N-type wafer. So if we follow the chart down, right, we get 1, 2, 3, 4 times 10 to the 15th of our donor impurity concentration. Why is it donor? Well, because we know it's an N-type wafer, meaning boron, which is at the third row in the periodic table, is a p-type donor, meaning it takes an electron and donates a hole. Okay, so we know that Nd is equal to 4 times 10 to the 15th atoms per centimeter cubed. If we now put everything together, right, and solve for T, right, so this is equal to this. Why is it equal? Because this is the concentration where we get the appropriate junction depth. We get, let's just take some steps. 4 times 10 to the 15th over N naught, which is 5 times 10 to the 18th. ln of that is equal to negative 4 times 10 to the negative 4th squared. Why? Because must convert to centimeters, right? So micrometers that we are given are, right, 4 times 10 to the negative 6 meters, which is 4 times 10 to the negative 4th centimeters, because there's 100 centimeters in a meter. We divide that by 4 times d, which we have solved for to be 2.96 times 10 to the negative 13th times t. We have all the values, right? So we could solve for t. So if we just kind of do some plugging and chugging, we will get that t is equal to 1.88 times 10 to the 4th seconds, or approximately 5.2 hours. And this could vary slightly based on your calculations and based on the value that you chose in the figure. But we got 5.2 hours for our time to do the diffusion. Now, this makes sense. We have a Gaussian profile. We're doing a deep drive in at a relatively stable temperature. Let's continue. Part B is asking us for the sheet resistance of the layer. To find the sheet resistance, we need to use something called Irving's curve. So this is figure 4.16. Irving's curve relates the surface concentration to the sheet resistant junction depth, that is in ohms per micrometer. So we know N naught, right? We know that N naught, the surface concentration, is given to be 5 times 10 to the 18th. If we then plug that in 2, 3, 4, 5, right, and we kind of follow it, we then have to look at NB. So in our case, we solved NB or ND, right, the impurity concentration, to be 4 times 10 to the 15th, where if we solve, which this line, which if we follow that roughly to this point, and if we trace that down, we get roughly 100, right? 100, 200, 300, roughly 330. RSXJ is equal to 330 ohms per micron. Here, obviously, we are looking for the sheet resistance, which we know XJ, it was given as the junction depth to be 4 micrometers. So we just divide 330 divided by 4, and we get a sheet resistance of 83 ohms per square. What is the dose in the layer? To find the dose, we use another equation that is given in the textbook, where the dose is equivalent to the surface concentration times the square root of pi times d times t. We know all of these values. 5 times 10 to the 18th, square root pi, d is 2.96 times 10 to the negative 13th, 1373 Kelvin, which is equal to 6.74 times 10 to the 14th atoms per centimeter squared. Very easy plug and chug. The dose tells us how many atoms there are per surface area. And finally, if we look at boron that is solid solubility limited, we can solve for the time and temperature for pre-deposition. So we are no longer looking for a Gaussian profile. We have to update our equations. And the updated equation is Q is equal to square root of 2 over square root of pi, the surface concentration, times square root of dt. Why can we reuse? Because Q is constant for a drive-in profile. You're not adding any dose, right? So the Q we have here can be used. We do actually know it. So we solve for D again, as we did earlier, and we could solve D is equal to 10.5 e to the negative 3.69 over 8.614 times 10 to the negative 5. And in this case, we have to actually choose either a time or a temperature and look at the other component. I think choosing a temperature is easier, and let's say our temperature is 1,000 degrees Celsius, which would correspond, to 1273 Kelvin. If this is inaccurate, we could adjust this. But for now, let's choose that temperature. It's a good benchmark. And at that temperature, we get D is equal to approximately 2.55 times 10 to the negative 14th. And if we then take this temperature and follow the solubility chart for boron, we get approximately 2 times 10 to the 20th. So this chart relates the concentration to temperature, where this is a solid solubility limit, meaning the concentration is actually limited. And like adding salt to water, as we increase the temperature, we can see how the solubility limit generally increases. So now we actually can connect everything together, plug this equation with all our known values. So Q we have solved to be 6.74 times 10 to the 14th. And that's equal to 2 over square root of pi. And we have to use the updated value from here, which is 2 times 10 to the 20th. And square root of dt, we could use 2.55 times 10 to the negative 14th times t. If we solve for t, the time, we get t is equal to 350.2 seconds, which is approximately 6 minutes. Notice this is an answer that is valid, but it's very short. Difficult to control. And we want higher time. Now this is my final question, which you could adjust yourself. How do we solve for a higher time? Well, you would choose a lower temperature to do diffusion, or in this case pre-position, more slowly. Time will increase. So for example, you could choose 900 degrees Celsius or even 800 degrees Celsius, though 900 should be plenty adequate. And that is question 4.3. Thank you.